first speaker today is Stefanie Zbinden, who will be telling us about how to use strong contraction to obtain hyperbolicity.
Hello everyone, thank you very much for the invitation. It's a pleasure to be here. And as we have seen already yesterday, and we'll doubtlessly see much more throughout the next 2 weeks, is that if we have a group and it has some non-positive curvature, then we can leverage this to prove results about our group. In particular, if we have a nice action on a hyperbolic space of that group, then we can use results and tools from hyperbolic groups and use them in our setting and prove equivalent results for our groups. And in general, the nicer the action, the more results we can prove. So in this talk, my goal is to show you how to construct a hyperbolic space where in some cases you have a universal WPD action, and don't worry if you don't know what that means, I will explain this later. And then talk about some work in progress with Cornelia Druccio and Davide Spriano, where we use this action to prove some structural results about certain groups. So perhaps one of the more prominent nice actions on a hyperbolic space are cylindrical actions. A group G is a cylindrically hyperbolic if it acts acylindrically and non-elementary on a hyperbolic space. So what does it mean to act acylindrically? Roughly speaking, it means that if we have 2 points, x and y, and if their distance is sufficiently large, then the intersection of their course stabilizer is sufficiently small. And we can say that, so in generally for the future of the talk, I'll just say an acylindrical hyperbolic action if I mean a non-elementary cylindrical action on a hyperbolic space. We say that an element G is a generalized loxodromic if it is a loxodromic for some acylindrically hyperbolic action. And here, loxodromic just means that its orbit can be viewed as a quasi-geometric. Okay. Now there is a reason why acylindrically hyperbolic groups are very well known, and the reason is twofold. Firstly, there are many groups that are acylindrically hyperbolic. For example, the mapping class group, relatively hyperbolic groups, many cat zero groups, many archin groups, and many more. And secondly, if we know that a group is acylindrically hyperbolic, then we can use this to prove several nice results about these groups. However, there is always a drawback and a line to walk between how large is my class of nice groups and how many things can I prove about these groups. And sometimes, if I want to prove stronger results, it's not enough to just say my group is acylindrical, but we want specific acylindrical actions that have somewhat nicer properties than being just acylindrical. An example of this is the following. If we have a group H, and we know it's acylindrically hyperbolic, and we have a finite overgroup G, is it acylindrically hyperbolic too? And the answer is, in general, we don't know. But if H had a largest acylindrical action, so a very nice acylindrical action, then we do know that G is also acylindrically hyperbolic. So somehow this encapsulates that, yes, an acylindrical action is nice, but somehow we want something more. And the something more we're going to talk about in this talk are universal WPD action. So an action of the group G on a hyperbolic space X is universal WPD if all generalized loxodromics of G X WPD in this action. And what does it mean to be WPD? This means, roughly speaking, two things. First, we want it to be loxodromic, and secondly, we want it to be acylindrically along the axis of this element. So if we want to understand which groups admit such a universal WPD action, one thing we might try to do is understand, well, if we have a group, what are our generalized loxodromics? Because if you don't know that, it might be hard to find a universal WPD action, let alone prove that it is a universal WPD action. Luckily, there is work from Stefanie, Bromberg, Fujiwara, and Sisto that help us greatly in this regard. Firstly, if we have an element G, such that the action of G on our, such that G is strongly contracting, and if you don't know what this is, just mean there's very nice hyperbolic-like features along this direction. Then, Stefanie, Bromberg, and Fujiwara showed that G is a generalized loxodromic. And not only did they show it's a generalized loxodromic, but they gave a specific construction called the projection complex, where they say, well, in this specific action, it is loxodromic. On the other side, we have a result from Sisto that says, well, if for somehow we ended up with a generalized loxodromic, through whatever means, then we know that it is Morse. For those of you who don't know what Morse means, it's another type of saying this direction is somewhat hyperbolic-like. So somehow, if we are in the case that Morse, being Morse, is equivalent to being strongly contracting, then we know what all our generalized loxodromics are, namely they're all the Morse elements. And now you must ask, well, this seems to be a very fringe condition. Some type of negative curvature along an axis is equivalent to some other type of negative curvature along an axis. When do we even have this? When do we have this? And the answer is, well, actually, we can call such spaces Morse dichotomous. And various well-known spaces have this property. Most notably, all cat0 spaces, all injective metric spaces, but we also have spaces of very much different flavor that satisfies, for example, certain infinitely presented C'1/6 small cancellation groups, and the list continues. So we know not only do we have many of these, they have some very different properties of each other. And now we can ask ourselves, okay, we found out what the generalized loxodromics are. Can we find a universal WPD action? For example, can we just use the Bestrina-Bromberg-Fujiwara machinery to get such an action? And the answer is, unfortunately, no. In this machinery, the space we get is very much dependent on the specific element here that we picked. And other elements will be acting elliptically. So, even though we would like to use this machinery and it was tried to extend, this was not very successful until recently, where even it was not known in any of these specific cases until roughly 2 years ago, when Petit, Spriano, and Saloom showed, well, at least we can do it for cat0 spaces. And this kind of gave a motivating push to say, well, okay, now we can do it for some. Can we do it for more? And the answer is yes, we can actually do it for all of them. So this was proved by both Petit Saloom by generalizing their result for cat0 spaces, and by me independently and simultaneously. And it says, if G acts on a Morse dichotomous space, acts geometrically on a Morse dichotomous space, then G admits a universal WPD action. And as I said, this was a result proven by both constructed the specific hyperbolic space but how the space is construction and what the space is different. So now I want to tell you about the space that I constructed, which I call the contraction space. And the definition might look slightly technical, but I'm trying to now give you an intuition why the definition is what it is, and why the definition is actually very intuitive and not very technical. And how we're doing that is we're going to go through several attempts, and then I'm going to tell you, well, maybe that's what you like to do, but then we'll find problems, and after several steps, we'll get to the actual definition. So first, we need a definition. And it says, a geodesic segment gamma is R-thin if for all triangles delta, where one side of them is gamma, we have that the following. So this is gamma and its midpoint, and we want that the distance between the rest of the triangle and the midpoint is at most r. So specifically, we don't want any of those triangles. We want them all to look maybe something like this. Now, we can say that gamma is thin.
Sorry, how do you compute distance? What does that mean? If gamma is very long and at the midpoint, so by distance you mean the infimum, or?
So we want that for all triangles. Yeah. This distance is small, so yeah, the infimum. But for a particular triangle, we can just use the normal distance from our space.
So the rest of the triangle enters the R bar on the midpoint, not both sides have to enter it?
Yes, the rest. Because otherwise, you could always have like a degenerate triangle, right? Where one side is a point. So at least one of the other two sides has to go through the midpoint. So we say it's thin if it is R thin for some R. And now, somehow this thinness, even though there are several quantifiers, is actually very much tied to hyperbolicity. Because you can say, well, a space is hyperbolic if and only if there exists a particular R0 that makes our triangles. So if we have a hyperbolic space, then for some specific R0, all our triangles are same. So it makes sense that somehow this should help us capture hyperbolicity. Okay. and this leads us to our first attempt. And to visualize it, this works on any graph, but we're gonna look at it in the case of the tree of flats. That is the Cayley graph of that free product z squared. Okay, so our first attempt is, well, we're gonna start with the graph and then we're gonna add an edge between x and y if and only if the geodesic between x and y is not thin. As I said, somehow you should think of thinness captures hyperbolicity, so you won't want to kill off everything. So now I want you all to stare at this a little bit and try to find out what the problem with this definition is and what it gives us in this case.
You create loops. Because you could be thin inside the region and not between points which are far away. But then you would just.
And we have to ask for a uniform R, right? Because otherwise. Yeah.
So here's something going on. Can you tell me any 2 points whose geodesic between them is not thin?
I mean, along the Morse geodesics?
No, any. With this definition, if you give me any 2 points, say.
You mean with respect to some R? You can always take R lambda, that's what you mean?
Yeah.
Yes.
Okay.
With this definition, this is somehow flawed.
No, I thought that you had an R implicitly in your definition already. So.
No. Okay. This is really for all R, and this is also why this definition gives you problems immediately, because, well, if you just take R to be the length of our geodesic, then everything is thin, and we didn't do anything, we don't get a hyperbolic space. So maybe we need to update the definition and say, well, it only counts as being thin if somehow this comes close here, but R is much smaller than the length of the geodesic, because otherwise it's just this point. So we can say, well, gamma is thin if it's R thin for some R, it's R thin if the length of gamma is at least 10R plus 1, and we have this. Okay. And then we can do an attempt 2, which is the same, but just with a slightly better definition of being thin. Now again, I want you to think a little bit what you think this does to our J-flats.
Sorry, you don't want the length of gamma to be much bigger than R, not just be bigger than just a fixed constant. It's enough to have this?
It's enough to have this.
Okay.
I mean, the constant depends on
right.
some things, and it's actually, you can replace it by a function, but this is kind of the minimum you need. So first we can try to think, well, what does it do to a flat, right? And if you look at 2 points in a flat, then somehow we can always just do such a triangle. That will be far away. So if we have any two points in the same flat, the geodesic between them is not thin. Well, this is a good start, because if we want to get a hyperbolic space out of this tree of flats, we at least we really want to collapse the flats. And that's actually the only thing we want to collapse, because it is enough to ensure hyperbolicity and acylindricity. So we can ask ourselves, well, if we have 2 points in faraway flats, what happens then? Is the geodesic between them thin? And the answer is, yeah, sometimes it's thin, but we have the following problematic situation. Namely, take 2 flats very far away from each other, x and y, and then take 2 points y prime and x prime, such that this is much bigger than this, and this is also much bigger than this, and somehow this is about 3 times as long as this. So the midpoint is somewhere here. Now, this geodesic might very well be thin, but this geodesic is not, because we can do something like this. So in our construction, we're adding an edge between x and y. But also I told you within the flats, we're adding edges. So suddenly the distance between x and y is at most 3. And here this was any 2 points in the space. So if we do this, we get something hyperbolic, but this is about the only positive thing we can say if we do this construction.
This is not a geodesic triangle if you already add the purple thing. Ah, that's before you add.
Yeah. Exactly. Okay, so any more questions? So we need to do something more clever. And somehow we realized, well, what was the problem here? And the problem here is we tried to negate thinness by just saying it's not thin. But it had potentially some subsegment that was thin. And because we collapsed it anyway, we collapsed the whole space. So instead of saying, well, the correct negation of being thin is if it's just not thin, it means the correct negation of being thin is you don't have any thin subsegments. So, definition, we say that a geodesic gamma is anti-contracting if it does not have any thin subsegment. And now we can repeat our procedure and do attempt 3 and say, well, we add an edge if it is anti-contracting. And if you look what this does to our tree of flats is, within the flats we said every segment is not thin. So every segment is anti-contracting, because if there's nothing thin, you can't have a subsegment that's thin. So we get that all our flats will be collapsed. On the other hand, if you look at an interval, then this is very much zero thin. If you look at this interval between the flats, because any thing going through the midpoint of this interval has to go through it. So if we take any geodesic in any 2 points in different flats, this geodesic can't be anticontracting because it has this thin subsegment. So what we get is the Bosser tree, and which is, I told you earlier, this is what we want to get from there. Now, if a construction works for one very specific, very nice example, well, maybe it doesn't work in general. And actually, I don't know whether it works in general, but if you want it to work in general, you can replace triangles with sixgons. And then we call this space that we construct the contraction space, and it has several nice properties that I'm going to tell you about now.
So your identifications produce a tree. But I mean, you have to replace the flats by. So, and your group Z, you probably Z2 still back something?
Yes. Because the thing is, the way we added edges is what kind of geodesic triangles or sixgons are there. And this is a property preserved by isometries. So whenever a group acted by isometries on our original space, it will act by isometries on the contraction space.
In the case of the relatively hyperbolic space, I get you get the cutoff space, am I right?
If the peripherals were nice enough, so like if there was no strong contraction in the peripherals, then yes.
Yes, of course.
Exactly. Any more questions?
So just the last question. So do we know that we always get at least a hyperbolic space using this with the triangle thing?
No, that's the thing we don't know.
You don't know whether it is hyperbolic.
Yeah. It's somehow in the proof, as soon as you have sixgons, everything works very nicely. But the reason why you need sixgons is somehow very silly. It's, well, if you have a triangle, and you're doing guessing geodesics to prove that your triangles are thin, so you have a point, and you have another point, and you want them to be close. And now, if this was not coned off, we know that it has a thin subsegment, and now we want to use this in this sixgon. And that's why we need the sixgons. Properties. The contraction space. And here I really mean take a geodesic metric space X and perform the procedure to get our contraction space X. So, firstly, the most important thing is that X hat is always hyperbolic. no matter what we start with. Okay? It's nice. And then we would also like to know that somehow the geometry of x and x hat somehow talk to each other. And actually, they do in the following way. If we have a geodesic in x, so then if we look at its image in x hat, so more specifically, we can look at gamma concatenated this natural inclusion that we have here, then this is, well, not a geodesic anymore, but at bounded Hausdorff distance from a geodesic. And moreover, this is a parametrized pulse. And it is a quasi-geodesic if and only if gamma was strongly contracting. This also is very nice because it tells us, well, you know, if I tell you can construct a hyperbolic space for any starting space, well, that's very easy, you just add all the edges, but this tells us, well, it's not only a hyperbolic space, but it's an interesting hyperbolic space. That as long as there was some strong contraction in our original space, it is not trivial. Because if we have a bi-infinite strongly contracting geodesic, it will map to a quasi-geodesic. That's bi-infinite, so it can't be bounded. Okay. Now, the second point is here. Is, well, what if we add a group and a group action? And as I explained before, if we have an isometric action of a group G on X, then this induces an isometric action of G on the contraction space. And if we assume that the action of G on X was proper, then we can say more nice things about the action of X hat. Namely, we can say the following, that if G is strongly contracting, the action of G on X hat is WPD. In particular, no, I just erased it. If we were starting with our merged dichotomous space, and if we're starting with a geometric action, then we will get a universal WPD action. So what this tells us, if the action of G on X is nice, so is the action of G on X hat. But we can also go the other way around. Namely, if G is loxodromic, then we know that it was strongly contracting. In particular, and we will use this later, we get the last point that if X hat is unbounded, then G is acylindrically hyperbolic. And this brings me to the last part of my talk, which is, well, okay, how can we use this nice action to actually prove structural results about the geometry of our groups? And how to do this? Following theorem. So if we have a group G, that acts nicely enough that is properly and co-boundedly, I'm gonna sweep some things under our here and say nice space. Then we have the following dichotomy. Either the group has linear divergence, that is, if we have any two elements x and y, and say with distance L, and the ball of radius L over 100 around the midpoint, then we can find a path from x to y that is linear in length of L and doesn't intersect this ball. So either we have this, or B, it is acylindrically hyperbolic. We also have that in this case, no asymptotic cone has a cut point, and in this case, all asymptotic cones have cut points. So it's really a statement that as long as you're nice enough, there is nothing in between. If one of your asymptotic cones have a cut point, all of them have to. And you might be wondering, what is a nice space? And for the purpose of this talk, you should think either injective or at zero.
I'm sorry, I'm not sure I understand really the statement, because when you say linear divergence, do you mean something that happens in the space or in G? Or X? Okay.
Let's say
X. Okay. And so then X on the other.
But
no, G is asymptotic.
yeah. Yeah. So when I say nice space, you should think either injective or cat zero. Even though I have to say for cat zero, this was already proved by Kent and Ricks. But our method will also prove that.
So what is an injective metric space?
It's if your balls intersect pairwise, they intersect commonly, roughly speaking. It's just a space where you have very nice controls on the geodesics.
So model and infinitive when reaching the spaces are model as well.
Okay. And now you can ask yourself, okay, how can we prove this using the contraction space? And well, if you look here, we already have one thing that tells us that our group is acylindrically hyperbolic. So what we know is that if somehow we perform our contraction space construction on X and we get something that's unbounded, then we are acylindrically hyperbolic. So On the other hand, if the diameter of the contraction space is 1, then this means that none of our geodesic segments were thin. Because otherwise there would have been a geodesic segment we didn't cone up. In particular, if we have 2 points, x and y, and we look at the all around them, we can always find a sixgon from x to y that doesn't intersect this ball. Because otherwise, it would have been fit. But now, if we use the geometry of the space, and this is why I said, oh, this only works for nice spaces, then we can somehow cut off the cups of these n-gon to then get a path that is linear in length and still is outside the ball. Because a priori, if you just follow the n-gon, this could have been huge, right? This could have almost gone to infinity here and back. But if you can cut them off at the right place, then suddenly this becomes linear. Okay. So somehow, the only problem you have left is, well, what happens if the diameter is less than infinity and more than 1? And this is actually, what you would like to say is, well, this doesn't happen. And if it doesn't happen, then you're done. But it's actually a very hard question, and we don't know whether this can happen. And we don't know. I personally think it shouldn't, but we can't prove it. But then we can go back to our definition, which is not here anymore. Well, we can go back to our definition of thinness and say, well, we said it was thin if there was no sixgon that entered that neighborhood. But instead of sixgon, we could have said 7gon or 8gon or 9gon. The only thing that was important is that our n was at least 6. So in fact, this gives us a whole collection of contraction spaces. Not a single one, but a whole collection. And then the important part of the proof of this theorem is to show, well, somehow we can compare the different contraction spaces with each other, and we can prove the following, namely that if the diameter of the n-gon contraction space is bigger than 1 for a sufficiently large n, then the diameter of the 6th one was infinite. So it tells us that if we can compare the different contraction spaces with each other, then we can actually get around this case and prove the theorem. Thank you very much.
Any more questions?
So in the theorem, is Morse dichotomous not nice enough?
No. Because we really want to be able to do this geometric cuts. And for example, I said you have certain infinitely presented small cancellation groups that satisfy this. So you could have a huge just relator here that builds your 6gon. And then there's no way you can shortcut this to a linear path. It's more about you want to have some kind of nice path system.
How far are we from knowing that asymptotic hyperbolicity is stable on the process.
I
Still, I mean, does it help? Like, do we? Because I thought at some point that I could be wrong that an asymmetric hyperbolic group has to have a modulistic in its telegraph, or
yes, if you're acylindrical hyperbolic, you have to have a Morse geodesic, but this is by far not enough to show that you're acylindrical hyperbolic. So we are very far from answering this question, and I think not every, like, the longer people have not been able to prove that it's even, if you go to index 2 supergroup, the more people think, well, maybe the reason we can't do it is because there is some kind of obstruction there.
Is A hat acylindrical? Do you know if A hat is X hat? Sorry, is are the inflections acylindrical or?
So it's non-uniformly acylindrical. So there were, in the definition of acylindrical, you have some constant. If you allow this constant to vary, then yes. But on the nose, we have like roughly computed example where you think it's not.
Oh, so there might be an example where there's an example where it's just X hat is just not as uniformly acylindrical.
Yeah, yeah. I mean, we haven't done the details, but if you look at Sam Shepard's cube complex example, then this would be the candidate to show it's not.
But, so if you start with an action which already has WPP element, then on the hyperbolic space, then the construction gives the same space. Am I right?
So yeah, if you start with a hyperbolic space, you'll not necessarily get the same space.
Because you
But
may still have.
you get the same space shrunk, so something that's quasi-symmetric to your original space. Because this thing is not only hyperbolic, but it's like uniformly hyperbolic. So it's like a uniform constant that it's delta hyperbolic for no matter what space X you start with.
So could you just reformulate what you said in the context of this theorem and cut points in all asymptotic cones?
Yes. So if G is acylindrically hyperbolic, that means that we have cut points in all asymptotic cones. And we show that, well, here, we have cut point in no asymptotic cones.
Okay, let's thank Stefanie again.